In this video, we're going to focus on solving solution stoichiometry problems. So let's start with this one. What volume of a 0.35 molar silver nitrate solution is required to completely react with 55 milliliters of a 0.24 molar sodium chloride solution? Now the first thing we need to do is write a balanced chemical equation. Silver nitrate is reacting with sodium chloride. And so what we have here is a double replacement reaction. Silver and chlorine, they're going to pair up in a 1-to-1 ratio. Silver has a positive 1 charge, chloride has a negative 1 charge. So silver chloride is simply AgCl. Sodium is going to pair up with nitrate, also in a 1-to-1 ratio. Sodium has a positive 1 charge, nitrate has a negative 1 charge. So the chemical equation is already balanced. Now, how can we use this information to find the volume of silver nitrate? If you want to find the volume of silver nitrate, start with the other substance, sodium chloride. Now keep in mind, molarity can be represented as moles per liter, which is what I'm going to do here. So a 0.24 molar solution means that there's 0.24 moles of sodium chloride per 1 liter of solution. Now let's multiply by the volume. We need to convert 55 milliliters into liters. To do that, simply divide 55 by 1,000. So that's going to be 0.055 liters. And now we could cancel the unit liters. Now the next thing we need to do is change the substance from NaCl to silver nitrate. And we can use the molar ratio to accomplish that. So 1 mole of NaCl will react with 1 mole of AgNO3. Now the next thing we need to do is convert moles to liters. We can do that using the molarity of the silver nitrate solution. So a 0.35 molar solution means that there's 0.35 moles of silver nitrate per 1 liter of solution. So now we can get rid of these units. And now we have the volume in liters. So it's going to be 0.24 times 0.055 divided by 0.35. And so you should get 0.0377 liters. And if you multiply that by 1,000, that's equivalent to 37.7 milliliters. So that's the volume of silver nitrate that's required to completely react with that solution. Now there's another equation that you can use to get the same answer. So anytime you see in a problem molarity, volume, you can use this equation. M1V1 is equal to M2V2. So on the left, I'm going to use M1V1 with reference to silver nitrate, and M2V2, I'm going to use it with reference to sodium chloride. So M1 is the concentration of silver nitrate, which is 0.35. We're looking for the volume of AgNO3. M2 is 0.24, and V2 is 55. So all we got to do is divide both sides by 0.35. So V1 is going to be equal to 0.24 times 55 divided by 0.35. And so this will give you the same answer, 37.7 milliliters. Now it's important to understand that if V2 is in milliliters, V1 is going to be in the same unit, milliliters as well. Number 2, 37 milliliters of a 0.29 molar potassium iodide solution is required to completely react with 42 milliliters of a lead nitrate solution. What was the original concentration of the lead 2 nitrate solution? So once again, let's begin with a balanced chemical equation. So lead nitrate reacts with potassium iodide. So we have another double replacement reaction. So lead is going to pair up with iodide. Now lead has a positive 2 charge, as indicated by the Roman numeral, and plus the fact that there's 2 nitrates attached to it. Iodide has a -1 charge. So lead 2 iodide contains the formula PbI2. Now we need to pair up potassium and nitrate. Potassium has a +1 charge. Nitrate has a -1 charge. If the magnitude of the charges are the same, you could simply write them together. So it's KNO3. Now our next step is to balance this reaction. Notice that there's 2 nitrates on the left side. So therefore we got to put a 2 in front of KNO3. And we have 2 iodide ions on the right side, so we got to put a 2 in front of Ki. And now the chemical equation is balanced. Now in order to find the original concentration of lead nitrate, let's start with the other substance, Ki. Now whenever you see the word molarity, you could write it as moles per liter. So a 0.29 molar solution means that there's 0.29 moles of Ki per 1 liter of solution. Now what we need to do is multiply by the volume in liters. So to convert 37 milliliters into liters, divide by 1,000. So that's going to make it 0.037 liters. So we can cancel the unit liters. Next, we need to change the substance from Ki to lead 2 nitrate. And we can do that by using the molar ratio. So for every 2 moles of Ki that reacts, 1 mole of lead 2 nitrate will react with it. So now we have moles of lead nitrate, and in order to get the molarity, we need to divide by liters. So we have the volume of lead 2 nitrate. It's 42 milliliters. If we divide that by 1,000, that's 0.042 liters. So now we can do the math. It's 0.29 times 0.037 divided by 2, and then divided by 0.042. So the concentration is 0.1277 moles per liter of lead 2 nitrate. So let's see if we can get the same answer using the formula M1V1, which is equal to M2V2. Now we can get the same answer, but we just have to be careful in the way in which we use it, because we need to incorporate the molar ratio in this reaction. M1V1 is going to correspond to this substance, lead 2 nitrate. M2V2 is going to correspond to potassium iodide. Now what you need to do is you need to exchange the coefficients with coefficients in this equation, but you got to reverse them. So this one is going to go over here, and the 2 is going to go on the other side. If you do it this way, the equation will give you the right answer. Now M1 is the molarity of lead 2 nitrate, which is what we're looking for. V1 is the volume of lead 2 nitrate, that's 42 milliliters. M2 is 0.29, and V2 is 37. So let's multiply 2 by 42, so that's 84. And then 0.29 times 37, that's 10.73. Now in order to get m by itself, we got to divide both sides by 84. 10.73 divided by 84, that's 0.1277. So as you can see, we get the same answer. So anytime you have a problem that has molarity, and volume, you can use this equation, but you need to write a balanced chemical equation. You need to find out what the molar ratio is and incorporate it into the equation. If you do that, then you could use the equation to get the right answer. Number 3, what mass of solid magnesium hydroxide can be produced if 45 milliliters of a 0.63 molar magnesium nitrate solution reacts completely with excess sodium hydroxide? Now we can't use the formula M1V1 equals M2V2 because we're not looking for molarity or volume, we're looking for the mass. Let's write a balanced chemical equation first. So we know that magnesium nitrate is reacting with sodium hydroxide. Magnesium is going to pair up with hydroxide, forming magnesium hydroxide. Magnesium has a +2 charge, hydroxide has a -1 charge. So to combine them, it's going to be Mg1OH2. Whenever you have multiple polyatomic ions in a compound, you need to enclose it using parentheses. So this is Mg OH2. Now the other product comes from pairing Na and NO3. They both have the same magnitude of charge, so we can write them in a 1-to-1 ratio. Now let's balance the chemical equation. So we have 2 nitrate ions on the left, therefore we need a 2 in front of NaNO3. So now we have 2 sodium ions on the right, so we need a 2 in front of NaOH. And now everything is balanced. So our goal is to find the mass in grams of magnesium hydroxide. Now, sodium hydroxide is the excess reactant. Magnesium nitrate is the limiting reactant. So therefore, we can base our calculations on the quantity of magnesium nitrate. So let's start with the molarity of magnesium nitrate. So it's 0.63 moles of MgNO32 per liter of solution. And now let's multiply it by the volume in liters though. So if you divide 45 by 1,000, it's going to be 0.045 liters. Now let's change the substance from magnesium nitrate to magnesium hydroxide. So it's a 1-to-1 ratio. So for every mole of magnesium nitrate that reacts, 1 mole of magnesium hydroxide will be produced. Now the last thing that we need to do is to convert moles into grams. So we need to find the molar mass of magnesium hydroxide. So in that formula we have Mg, 2 oxygen atoms and 2 hydrogen atoms. So the atomic mass of Mg is about 24.305 and oxygen is 16, hydrogen is 1.008. So if you add up all these numbers, you should get 58.321 grams per mole. So that's the molar mass of magnesium hydroxide. So 1 mole of magnesium hydroxide has a mass of 58.321 grams. And so now we can get the answer. It's 0.63 times 0.045. And then we got to multiply that by 58.321. So the mass is 1.65 grams of magnesium hydroxide. So that's the mass that can be produced in this reaction. That's the theoretical yield. Number 4. What mass of solid calcium phosphate can be produced if 73 milliliters of a 0.17 molar sodium phosphate solution is mixed with 58 milliliters of a 0.24 molar calcium chloride solution? So in this example, we don't know which one is the limiting reactant or the excess reactant. we're given the information for both reactants. So therefore, we need to identify the limiting reactant. What I'm going to do though is I'm going to take the information of each reactant and find out how many grams of product each reactant can produce. The reactant that produces less product is the limiting reactant. And the quantity of less product will be the actual mass of solid calcium phosphate that will form in this reaction. So we can get the answer and identify the limiting reactant doing it that way. So first we need to write a balanced chemical equation. We're not given the formula of sodium phosphate, so we need to come up with it ourselves. Sodium has a positive 1 charge. Phosphate has a -3 charge. So make sure you study the polyatomic ions. So sodium phosphate is Na3PO4. Next, we need to write the formula of calcium chloride. Calcium has a positive 2 charge. Chloride has a -1 charge. So the chemical formula is Ca1Cl2, or simply CaCl2. Now sodium is going to pair up with chlorine, and they have the same charge, so it's just going to be NaCl. Calcium is going to pair up with phosphate. Calcium has a positive 2 charge, phosphate has a -3 charge. So they're going to combine in this way. It's going to be Ca3PO42. So that's the precipitate in this reaction. Next, we need to balance the chemical equation. So we have 2 phosphate ions on the right side, so we need a 2 in front of Na3PO4. And now we have 6 sodium ions, so we need a 6 in front of NaCl. And there's 6 chlorine atoms now, so we need to put a 3 in front of calcium chloride. And now everything is balanced. Now let's start with sodium phosphate. Let's see how many grams of calcium phosphate can be produced if all of the sodium phosphate reacts in this chemical reaction. So this problem is going to be similar to number 3, but we're just going to follow that same process with each reactant. So I'm going to start with 0.17 m. So there's 0.17 moles of sodium phosphate per liter of solution. And next, let's multiply it by the volume in liters. 73 milliliters is the same as 0.073 liters. Now let's convert sodium phosphate into the product, calcium phosphate. The molar ratio is 2 to 1. So we're going to put 2 moles of Na3PO4 on the bottom, so that these 2 units will cancel. And we're going to put 1 mole of calcium phosphate on top. Now the next thing that we need is the molar mass of calcium phosphate. So there's going to be 3 calcium atoms in that compound, 2 phosphorus atoms, and 4 times 2 is 8, so 8 oxygen atoms. The atomic mass of calcium is about 40.08. Phosphorus is 30.97, and oxygen is 16. So the molar mass is 310.18 grams per mole. So 1 mole of calcium phosphate has a mass of 310.18 grams. So now let's get the answer. 0.17 times 0.073 divided by 2 times 310.18. So the mass produced is going to be 1.925 grams of calcium phosphate. So I'm going to highlight that in green. And I'm going to highlight this in green. So just to keep track that this mass came from this reactant. It's based on sodium phosphate. Now let's follow the same procedure, but with calcium chloride. So let's start with the molarity of calcium chloride. So it's 0.24 moles per liter. And now let's multiply by the volume, which is going to be 0.058 liters. Now the molar ratio between calcium chloride and calcium phosphate is 3:1. So we're going to have 3 moles of calcium chloride on the bottom and 1 mole of calcium phosphate on top. Now the last part is going to be the same. The molar mass of calcium phosphate is not going to change. It's going to stay 310.18 grams per mole. So now let's get the answer. It's 0.24 times 0.058 divided by 3 multiplied by 310.18. So this is equal to 1.439 grams of calcium phosphate. So therefore, the theoretical yield, the actual mass of calcium phosphate that can be produced, the most that we can get in this reaction, is not 1.925. It's the smaller of the two values. It's 1.439. So this is the answer. That's the theoretical yield of calcium phosphate. Now the reactant that gave us that answer, that's the limiting reactant. Calcium chloride was a substance that led us to this answer. Sodium phosphate is going to produce more product than what we should get in this reaction, so therefore this is the excess reactant. Calcium chloride is going to run out first. So that's how you can identify the limiting reactant and at the same time get the theoretical yield. But the answer to this problem is 1.439 grams.